Welcome to Calculus 1. In this video, we're going to talk about what's so-called the Rolle's theorem and the mean value theorem. Okay. It turns out Rolle's theorem gives us condition that guarantees the existence of an extreme value in the interior of a closed interval, rather than just at the endpoints. In the prior video, where we noticed that the relative maximum or the minimum can occur at the endpoints, but Rolle's theorem give us a guarantee where at least an extreme value, okay, will be in the interior of a closed interval. So Rolle's theorem says that let function f be a continuous function on a closed interval from a to b, and it's also differentiable on the open interval from a to b as well. If f of a is equal to f of b, okay, so that means I got two y values that are the same with the two different x value plugged into the function. Then there exists at least one number c in that open interval from a to b, such that f prime of c is going to equal to 0. Okay, so I gotta have two y values that are the same, okay, inside that interval. If that happens, then I can find a number c in the interval where f prime of c is equal to 0. Alright, so let's check it out. Alright, I have an open interval from 1 to 2. Okay, I need to find all the values c in the interval such that f prime of c is equal to 0. So if I plug in 1 here and plug in 2 here, okay, what I will find out is the two y value will be the same, both will be 0. Okay, so they tell me in this interval from 1 to 2, okay, they're gonna be a number c such that f prime of c is equal to 0. So let's take a derivative of our function. This is a parabola, but I'm only looking at it from 1 to 2. So that will give me 2x minus 3. Alright, so my derivative equal to 0, so I can find the critical value. And that will be equal to 3/2. So notice that the 3/2 is in the interval, okay, from 1 to 2. Okay. And this 3/2 is actually a critical number. So that tells me that this 3/2 is actually an extremum. Okay, because Rolle's theorem guarantees, okay, this critical number, this c is going to be my extremum. And we can graph it too, but it's going to be kind of hard to see. If I just do x squared, let me do it like this. X squared minus 3x plus 2. Oops. Minus 3x plus 2. Alright, I'm going to graph it under the standard window so you and I both see this is a parabola. Alright, I only want to look at from interval from 1 to 2. So I go to my window. I'm going to do a little bit, I'm going to do from 0 to 3 so I can have 1 and 2 in the middle of it. Okay, so that means from 1 to 2, okay, f prime of c is equal to 0, so that creates a horizontal, it creates a horizontal tangent line right here. If I would make my window smaller, let me do from -1 to 1 on the y value part. Let me see that. There you go. Right here. 3/2. 1.5. Okay, what's in between them? Okay, so that would be my relative extremum. Okay, from between the interval from 1 to 2. Alright, so that is my value c. Alright, let's try another example. The function is supposed to be x to the 4th minus 2x squared. Okay, we're typing it wrong. Alright, so let's plug in -2 and 2 and see if I plug in -2 and my right point 2, it will actually turn out to be 8. Alright, so the two y values are the same, which is 8. So that means there exists a number c inside the interval between -2 to 2. Okay. So let's find that number. If I take a derivative of my function so I can find the critical value, derivative of x to the 4 will be 4x to the 3rd minus 4x. Alright, if I set it equal to 0 to find my critical value, I'm going to go ahead and factor this one out. So that will be x squared minus 1. So that will be 4x times x plus 1, x minus 1. Alright, so set each factor equal to 0. I'm going to have critical number x equal to 0, x equal to 1, and x equal to 2. Excuse me, x equal to -1, positive 1, and a 0. Alright. So, since these three critical values, okay, are in the interval, that means these three critical values is going to be my extremum inside the interval as well. And of course we can actually graph it and see. Alright, so that's what the Rolle's theorem says. You know, if I can, inside the interval, if the y value are the same, okay, then there exists at least one number c that is your extremum. In this example, I actually have 3 of them. Alright. Now let's take a look at one of the most powerful theorem in calculus. It's called the mean value theorem. We use a lot of mean value theorem as we use it as for proofs, okay, for other theorems, or we can directly use it for problem solving. Okay, the mean value theorem. Just if you just think about the word mean, is actually like the word average. Okay, the mean value theorem here says if my function f is continuous on a closed interval a to b, and it's also differentiable on the open interval from a to b, then there is at least one number c in the open interval such that f prime of c, okay, is equal to f of b minus f of a over b minus a. And here is the alternative form. So what I'm saying is, okay, what I'm saying is f prime of c, which is the slope of my tangent line, okay, the slope of the tangent line is going to be right there in the middle of the slope of the secant line. Okay, so the f of b, f of a will be my secant line. So my slope of the tangent line is right here in between them. Okay, that's what this theorem is saying, the mean value theorem. So it's not necessarily saying it's exactly halfway between A and B. Okay, that's not what it's saying. Alright, because these curves, you know, these graphs are, you know, has curvature. So what it's saying is it's actually between, okay, sitting in between these two numbers, or right in the center of the secant line. And I can move this line all the way up. Okay, so eventually, if I move this secant line all the way to match up with the slope of the tangent line, okay, that tells me that point is the, you know, that's where the f prime of c is equal to the slope of the tangent line. Alright, so a lot of times these graphs kind of does help us to understand a little bit. Alright, let's see how we can use the mean value theorem in a problem here. Alright, I want to find all the value of c in the interval from 1 to 4, such that f prime of c will equal to f of 4 minus f of 1. So this is 4, this is 1. Okay. Alright, so f of 4 minus f of 1 over 4 minus 1. So we're going to subtract the 2y value divided by the x value. So that will give me my slope of the secant line. So what it's saying is, what is that number? Okay, the slope of the tangent line is equal to the slope of the secant line. Okay, what is that value C? Alright, so let's do this part first. F of 4 minus f of 1. The slope of the secant line. F of 4 minus f of 1 over 4 minus 1. That would be 5 minus 4 over 4. Substitute 1 for x, minus 5 minus 4 over 1. Whole thing over 4 minus 1. Then I believe that's going to be positive 1. Alright, so slope of secant line is 1. Alright, f prime. Okay, let's figure out what f prime is next. F prime of x, derivative of phi is 0. Okay, minus 5 over 4. Minus 4 over x, and I think that's gonna be factor out, so I think that's gonna be 4 over x squared, because a factor 4 is still up there. Alright, so by the mean value theorem, okay, there exists at least one number c in the interval such that f prime of c is going to equal to 1. Okay, so this thing come out to be 1, and my f prime is 4 over x squared. So to find that number c, I set it equal to 1. My f prime, okay, to find this x value here, I will set my slope of a tangent line equal to the slope of a secant line. So if I use a cross product here, that would be 4 equal to x squared, and x is going to equal to, take a square root on both sides, positive negative 2. Alright, now negative 2 is not in the interval from 1 to 4, but positive 2 is. So that will tell me that c is equal to 2 inside the interval from 1 to 4. There you go. So what would this c be? Okay, when the slope of secant line equal to the tangent line is when what? When that number x value is 2, or c equal to 2. Alrighty, so that's row theorem and the mean value theorem.